Hello friends and my dear students, I welcome you all to my channel. I hope you are all well and your studies are also going on well. This is part 1 of the next chapter, that is symmetry. In this chapter, the chapter name in the textbook of author RS Aggarwal is actually Reflection Symmetry and Rotational Symmetry. So I've written in short, mentioned as the title, symmetry. So this is part 1 video where I will discuss about only the reflection symmetry of figures, and I will explain some example symmetrical figures and solve most of the problems of exercise 18A, which is based on the reflection symmetry. So this video is part of the playlist CBSE Maths for class 7 following the textbook of author RS Aggarwal. If you are new to my channel or not yet subscribed, or if you are watching my videos for the first time, I highly and strongly request and suggest that you please support me by subscribing to my channel, and also please do not forget to press the bell icon so that you will be notified by my future videos. So let's get started with this video. Okay, so I have my rough notes, quick notes prepared on the left hand side. I will provide a link. I will mention the link of the PDF of the quick notes in the description below, so you need not take any screenshots of my notes. And on the right hand side, I will discuss any concepts and will solve the problems from exercise 18A. Okay, so we will discuss about reflection symmetry of figures. Now, reflection symmetry is symmetry about a line. So a figure is said to be symmetrical about a line L if it looks identical on both sides of L. So let's say we have a line. The line could be the position and the orientation of the line could be anything. It could be horizontal, vertical, it could be inclined at an angle. So let's say to be very I'm taking a very basic example. This is the line L. Now, if there is if a figure is symmetrical about this line, let's say there is a I'm drawing a random figure. Let's say this figure. I don't know what kind of figure is this, but I will try to make it symmetrical. Now, so I hope it is looking more or less symmetrical. So this figure, whatever this figure is, let's say this figure is A, B, C, D, E and F, and this is the line. So we can see that more or less this figure A, B, C, D, E, which is having 6 sides, A, B, C, D, E, F, it is looking more or less, let's assume that it is more or less symmetrical about the line L. The vertical line is L. So this is known as reflection symmetry. That is, now what does it mean that this figure A, B, C, D, E, F is symmetrical about the line L, and that it looks identical on either side of the line L or on both sides of the line L. On the right hand side of the line L, you see the figure. Let me see if I can. You see this figure, this figure on the right hand side, and on the left hand side you see this figure. So this looks identical. Now, what does identical means? Identical means they are congruent. The figure is looking identical on both sides. I mean, it looks identical on both sides of about the line, which means that the figure, some part is on the one side of the line and the other part is on the other side of the line. Both the parts of the figure are congruent. That is what it means, that the figure looks identical on either side of the line L. Now this L, it could be horizontal, vertical, or it could be inclined at any angle. Does not matter. The figure will look. The figure will have some part. Basically, one half of the part of the figure will be on one side, and the other half will be on the other side, and the two halves will look identical. That means looking identical means they are congruent. Now, let's say if I take another example, If I take a very specific example, this is, let's say, now, and this line L is known as the line of symmetry. So let's say L be a line of symmetry, and we have a triangle. Let's say it's a this kind of triangle. Let's say, and this is symmetrical about the line L. Now clearly, so the right hand. So let's say this triangle is ABC. The actual original figure is ABC, which is a triangle. Now it is symmetrical about the line L. That is, let's say this point is the line of symmetry L. Let's say it is passing through A, the vertex A, and it is intersecting the side BC at point O. Now, when I say the triangle ABC is symmetrical about the line L, I mean that triangle AOC will be congruent to triangle AOB. This is what it means, that the triangle ABC looks identical on either side of the line of symmetry, or this line L. That is, on either side, whatever part is the part for this example, the line of symmetry is vertical. So the part of the triangle ABC on the right hand side of the line L, that is triangle AOC, is looking identical to the part of the triangle ABC on the left hand side of the line of symmetry L, which is the triangle AOB. And so triangle AOB and triangle AOC looks identical, which means they are congruent. So this is the basic idea of reflection symmetry, that is, a figure looks identical about a line on both sides, and that line is known as the line of symmetry. Now let me check if everything is fine. Okay. Now let's study some examples, some example figures, and see what are their line of symmetry. So line of symmetry means the line about which the figure is having a reflection symmetry. So the first one example is line segment. The first is line segment. Okay, the first is line segment. So if you have a line segment, now the line segment could be, what is a line of symmetry for a line segment? The line segment could be, I mean, its position could be, and orientation could be anything. In the notes, the line segment is AB, which is horizontal. Now I can take any line segment. Let's say this is a line segment. This is a line segment. Let's say AB. Now, what will be the line of symmetry of this line segment AB? That line will be the perpendicular bisector of the segment AB. That is, first to take the midpoint of the segment AB, and then if you draw a perpendicular line, let's say this midpoint is O, and if you draw a perpendicular line passing through the point O, this line, sorry, it missed the midpoint anyway. So this line, this is perpendicular, this line, let's say L, this line is the line of symmetry for the segment AB. And you can clearly see that the two parts on either side of the line L are the segments AO and OB, and clearly we know that AO will be equal to OB. AO will be equal to OB. Now, why the segment AB? When can I say that the segment AB is symmetrical about the line L? If the segment AO is congruent to the segment OB, because as I said, the part of the figure on both sides has to be congruent. That is when, if two figures are congruent, then they look identical. So for a segment AB, its perpendicular bisector is the line of its line of symmetry. Okay. Next is isosceles triangle. What is the line of symmetry for an isosceles triangle? Let's say we have an isosceles triangle. My figure will not be perfect, but I am trying to draw the figure as perfect as possible. So let's say this is an isosceles triangle ABC, where the two equal sides are AB and AC. So definitely the angle B will be equal to angle C, as the sides opposite to the equal angles in an isosceles triangle are equal. Okay. Now what will be the line of symmetry for this isosceles triangle ABC? It will be the line. It will be the angle bisector of the bisector of the angle A. Why A? Because the angle A is included between the two equal sides of the triangle of the isosceles triangle ABC. It is important. For an isosceles triangle where AB equals to AC, you have to consider the including angle, that is the angle included between the two equal sides. In this figure, I have considered AB equals to AC. So the angle including between AB and AC is the angle A. If you bisect the angle by a line, let's say this is the line that is bisecting the angle A, and let's say this line intersects the opposite side BC at point O, then this line, and say this is Q. So the line AOQ or the line L is the line of symmetry for this isosceles triangle ABC, because in this case, because you will see the triangle AOC will be congruent to triangle AOB. That is, the triangle AOC will looks identical to the triangle AOB, and the triangle AOC, the original figure was triangle ABC, and the triangle AOC is the portion of the triangle to the right hand side of the line of symmetry L, and the triangle AOB is the portion of the original figure to the left hand side of the line of symmetry L, and they are identical or they are congruent. Hence, the isosceles triangle ABC is symmetrical about the line AOQ, which is the line L. Okay. So so this was one line segment, and this was number 2 isosceles triangle. Now let's see what is the line of symmetry for a kite. What is the line of symmetry for a kite? Okay, so what is a kite? A kite is a quadrilateral, that is a polygon with 4 sides, where the diagonals intersect each other at right angles. Let's say I have a diagonal, this is a diagonal, and another diagonal, let's say they intersect at right angles, let's say this, such that now let's say now if you join the endpoints of the diagonals, let's say if you join these 4 points, that is the 2 endpoints of the diagonals, let's say these endpoints are A, B, C, D, and if you join them, now the diagonals intersect each other at right angles. I didn't say that the diagonals bisect each other. The diagonals intersect each other at right angles, such that you will have BC equals to CD, and AB equals to AD. You draw the 2 diagonals. AC and BD are the diagonals. If you draw the diagonals AC and BD such that they intersect at right angles, and also BC equals to CD and AB equals to AD, then the figure ABCD will be a kite, and it will be symmetrical about the line L, which is the line of symmetry. I'm referring capital L as the line of symmetry for all figures. So in this figure, kite L will be, let's say the diagonals intersect at O, will be the line AOC, straight line or line AOC. Okay, now why AOC, why not BOD? You can clearly see why A is line of symmetry. I am in short abbreviating line of symmetry as LOS. So let me write line of line of symmetry as LOS. So uh, L that is AOC will be the line of symmetry, and why not BOD? Why not BOD is a line of symmetry? Always remember that for a kite, the longer diagonal or the larger diagonal is the line of symmetry. It is never the smaller diagonal. But and also remember that in a kite, the two diagonals the two diagonals are never uh, equal. If the two diagonals are equal, mm, if the two diagonals once again, can the two diagonals be equal? Yeah, maybe the two diagonals can be equal. Anyway, so if the two diagonals are equal, let me check, can a kite have two diagonals equal? I mean, if I this, okay, yeah, I think the diagonal can have two equal diagonals. The concept is that the larger diagonal, a kite will always be symmetrical about the larger diagonal, and if the diagonals are equal, no, sorry, it is not the fact that a kite is symmetrical about its larger diagonal, because it can be the case that the diagonals in a kite are equal. In that case, I mean, I can have a kite like this. Let's say this is a diagonal, and let's say I have approximately, if this is the midpoint, then I can have this. So A, B, C. So here, as you can see, A, B, in this kite A, B, C, D, the diagonal AC and BD are more or less equal, but still it is a kite. And also see that this kite is symmetrical about the diagonal AC, not BD. Now why AC? Why AC? Why not BD? Okay, so I think the diagonal why it is AC? Why not BD? Clearly because now the smaller sides, we can clearly see that AC and BD. Now if AC on the larger diagonals, in the second kite figure, the diagonals are equal length. So, but it is still not symmetrical about the diagonal BD. It is symmetrical about the line diagonal AC. Why is it so? Because the diagonal BD. Anyway, I'm sorry, I'm not able to give the proper reasoning why it is not symmetrical about the diagonal BD. As you can clearly see that it is symmetrical about the diagonal AC in both the figures, in both the kite figures. So it is symmetrical about the line about the diagonal AC, and why exactly it is not? From the figure, you can easily figure it out by which diagonal the kite will be symmetrical. But if you try to give a mathematical reasoning, it has to have a mathematical reasoning, which I cannot figure it out right now. I will think about it later on. I will talk about that in some later future videos. I'm sorry, I cannot give the proper reasoning why. How can we decide by which diagonal a given kite is symmetrical? Okay. Now, definitely, now, no, wait a second. Uh, mm, okay. Anyway, so I can't think of the proper reason why. How can we say by which diagonal a kite is symmetric? But it will be symmetric about one of its diagonals. And in this figure, in this example figure, ABCD, the kite, we can clearly see that the diagonal AC is the line of symmetry. So that was kite. Even though I was not able to properly explain it. I'm sorry for that. A semicircle. Uh, a semicircle. Now, a semicircle. What is a semicircle? Now, I won't be able to draw a semicircle properly. So you have a diameter. So this is a, let's say this is the diameter of the of a circle. This is the center AOB. So this is a kind of semicircle. This is a semicircle having the diameter AB and the center at O. Now, if you draw a perpendicular line perpendicular to the diameter AB, which passing through the center O, this line will be the line of symmetry of this semicircle. So this is perpendicular. So this is the line of symmetry for the semicircle. Let's say if the semicircle intersects this line as C, the semicircle is ACB. The semicircle ACB is symmetric about the line L, where the line L is perpendicular to the diameter AB and it is passing through the center O. So that is the line of the symmetry for a semicircle. That is the line of symmetry. Now, okay, so one more thing, you must understand that how many lines of symmetry are there for each figures that we are discussing. For a line segment, there is only one line of symmetry, exactly one line of symmetry, because the line of symmetry for a line segment will pass through the midpoint of the line segment, and that line will be perpendicular to the segment AB, and that will be a unique line. So a line segment has only one line of symmetry. For an isosceles triangle, it is also for an isosceles triangle ABC, where AB equals to AC, it also has only one line of symmetry, which is the line that bisects the angle A, and which bisects the angle A. And so in this example, the line AOQ is the line of symmetry for this isosceles triangle ABC, where the angle B is equal to angle C, and the line of symmetry is bisecting the angle A. So it also has one line of symmetry. For a rhombus, for a kite also, it has only for a kite also it has only one line of symmetry, and it will be one of the diagonals. Now, exactly which diagonals, I cannot think of the proper reasoning which diagonals, but it will be one of the diagonals. So a kite has one line of symmetry. A semicircle, number 4, and a semicircle will also have one line of symmetry, which is the line passing through the center O and which is perpendicular to the diameter AB. Okay. 5, isosceles trapezium. 5 is isosceles. 5 is isosceles trapezium. Now, what is a trapezium? What is a trapezium? A trapezium is a quadrilateral that is having 4 sides, a polygon having 4 sides, such that two sides are parallel to each other, and they may not be equal, but 2 sides are parallel to each other. Let's say this is side AB and this is side CD, and now if you join A and C, and B and D, this is a ABDC is a trapezium, where AB is parallel to CD. Only two opposite sides of a trapezium are parallel. So AB is parallel to CD, and uh, AB is parallel to CD, and also the other two opposite sides are not parallel. That is, AC is not parallel to BD. So this is a trapezium. Now, if it is the case that in the trapezium, if the two opposite sides which are not parallel, if they are equal, then this is a isosceles trapezium. That is, in this trapezium, ABCD, ABDC is an isosceles trapezium where the opposite sides AB and CD are parallel to each other, and the other two opposite sides AC is equal to the other two opposite sides are equal. That is, AC is equal to BD and AB is parallel to CD. This is an isosceles triangle. Now, for this isosceles trapezium. Now, for this isosceles trapezium, what will be the, sorry, my figure is not really looking like an isosceles trapezium, but just assume that it is an isosceles trapezium where AC is equal to BD and AB is parallel to CD. For this isosceles trapezium, the line of symmetry will be, you join the midpoints of the two parallel sides. The two parallel sides are AB and CD. You take the midpoint of AB, you take the midpoint of CD, and if you join the line, so this line is the line of symmetry for the trapezium, isosceles trapezium ABDC. So if this is E and this is F, we have AE equals to BE and CF equals to DF. So this line, now the L will be the line of symmetry of the trapezium, and also you can clearly see that there is only one line of symmetry for an isosceles trapezium. There is only one line of symmetry. Okay. Rectangle. A rectangle, as you know that rectangle. So let's say, how do we draw a rectangle? Let's say if I can draw properly a rectangle or not. Okay. So let's say if this is a rectangle. In a rectangle, you know, let's say A, B, C, D is a rectangle where the two opposite sides are parallel, and the two opposite sides are parallel and equal, but two adjacent sides are not equal. I mean, they could be equal, but not necessarily they should be equal. And of course, all corner angles are perpendicular or 90 degree. So this is a rectangle. So what are the line of symmetry of this rectangle? A rectangle has two lines of symmetry, and those two lines are, if you join the midpoints of the two opposite sides, let's say AB, let's say the midpoint of AB is E and the midpoints of DC is F. If you join these 2 points, then this line L1 will be a line of symmetry of this rectangle ABCD, because the ABCD will look identical on both sides of the line. Let's say this is Q of the line EFQ. Another line of symmetry will be, if you join the midpoints of the other two opposite sides, that is, let's say this point is G, and this point, the midpoint of BC is H and midpoint of AD is G, and if you join G and H, this line will be the second line of symmetry. The second line of symmetry, let's say this is S. So the line GHS, that is L2, is another line of symmetry of the rectangle ABCD. There are no other line of symmetry. So a rectangle has two lines of symmetry, which are the lines joining the midpoints of the two of the opposite sides. Okay, so this was a rectangle. Now rhombus. Rhombus. So we know that what is a rhombus. What is a rhombus? What is the structure of a rhombus? In a rhombus is a quadrilateral where all the sides are equal, all the four sides are equal, and the diagonals bisect each other at right angles. So if you take the diagonals bisect each other at the right angles, and the diagonals need not be equal. So let's say I have let's say this is a one diagonal, the diagonals will bisect each other at right angles. Bisect each other at right angles. So this is a midpoint. If I say take another diagonal, these two diagonals, let's say one diagonal is BD and the other diagonals is AC. So these AC and BD are the two diagonals of the rhombus, and they bisect each other at right angles. So now AB CD will be a rhombus. ABCD is a rhombus, and in a rhombus, the two lines of symmetry are its two diagonals. So a rhombus is symmetrical about its two diagonals. So this rhombus ABCD is symmetrical about the diagonals AC and BD. Okay. So always remember that in a rhombus is always symmetric about its two diagonals. Okay. Now square. The square is square. It has the maximum number of lines of symmetry. So if you have a square, let's see if I can. If you have a square, oh sorry. I'm trying to draw a square. Can I draw a square? Okay, so this is a square. Let's say A, B, C, D. What are its line of symmetry? What are its line of symmetry? It has 4 line of symmetry. The two diagonals, their line of symmetry. The two diagonals, we know that in a square, all the 4 sides are equal, and the corner angles, all the corner angles are 90 degree. So the two diagonals AC and BD, their line of symmetry. Also, if you join the midpoints of the opposite sides, those two lines are also line of symmetry. So if this is the line L2 and this is a line L1, so L1 and L2 are also line of symmetry of the square ABCD, and also the two diagonals AC and BD. So a square has 4 lines of symmetry. So a square has 4 lines of symmetry. A rhombus has 2 lines of symmetry. That is, the two diagonals of rhombus are its line of symmetry. A rectangle has 2 lines of symmetry. That is, the lines joining the midpoints of the opposite sides. An isosceles trapezium has a single line of symmetry. That is, the line joining the midpoints of the opposite parallel sides. Semicircle has one line of symmetry, which is the line that line is perpendicular to the diameter AB and passing through the origin, center of the circle. A kite has one line of symmetry, which is a diagonal. Now, which exact diagonal in a kite it will be the line of symmetry? I cannot figure it out, the mathematical reasoning. If I can, I will let you know in some future videos. In an isosceles triangle, it has one line of symmetry, which is the line bisecting the angle that is being included by the two equal sides. And for a line segment, it has also one line of symmetry, which is the perpendicular bisector of the segment AB. Okay. What we have? Okay, so equilateral triangle. Equilateral triangle, if you have, and you know that in equilateral triangle, all the sides are equal and also all the angles are equal. So I don't know whether I will be able to draw properly an equilateral triangle or not. Let me see if I can. So let's say more or less this is an equilateral triangle. So how many lines of symmetry it has? An equilateral triangle has 3 lines of symmetry. What are those 3 lines? They are the bisectors of all the angles. Now, what do you mean in a triangle? What do you mean the bisector of the angle A? A bisector of the angle A is a straight line. It's a straight line passing through the vertex A definitely, and it is bisecting. The angle A. That is, if this line, let's say this is AS. So the line AS is bisecting the angle A of the triangle ABC. So this is equal to this. Another, so similarly, since there are three angles, there will be three angle bisectors, and so there are three lines of symmetry. All the angle bisectors of a triangle are the line of symmetry in an equilateral triangle. Similarly, I will have, if I draw the bisector of the angle C, it will look something like this. So this is also, this angle will be equal to this angle, as this line is bisecting the angle C. Similarly, if I bisect the angle B, the line will look something like this, and this angle will be equal to this angle. So there are three angles in a triangle, and if the triangle is an equilateral triangle, that is all the three angles are equal or the sides are equal, then the angle bisectors, we have three angles in a triangle, so we will have three angle bisectors. All the angle bisectors in an equilateral triangle are line of symmetry. So an equilateral triangle has three lines of symmetry. Okay. Now circle, I think this is the last one. So a circle, what is, so if I have a circle, what are the line of symmetry of a circle? It will be all the diameters that you can possibly draw. There are possibly infinite number of diameters, or any diameter. So let's say if this is the center of the circle, O, so you draw any diameter. This can be a diameter. Let's say this is AOB. So the circle will be symmetrical about the diameter AOB. If you draw another diameter, let's say this be, let's say this be COD, then the circle will also be symmetric about the diameter COD. So a circle is symmetric about all its diameters. Okay. Now there are some letters in English alphabets which also have reflection symmetry. That is, they are symmetric about a line. And these letters are A, B, C, D, E, H, I, M, O, T, U, V, W, X, Y. I have drawn some letters and have shown the line of symmetry. For example, the letters A, I will not draw the letters. The letter A has a single line of symmetry. That is, if this is A, if you bisect this angle, the bisector of this angle will be the that is somewhat like this. This line will be the line of symmetry for the letter L. For B, you can see the B. If you the B, the line of symmetry will be the horizontal line. So if this is B, the line of symmetry will be the line, the horizontal line, which is passing at this how do I say? If you consider this side, of the B as a straight line, of course it is a line segment. You can consider the perpendicular bisector of this side of the letter B to be its line of symmetry. Okay. So similarly, you can see that letter C has one line of symmetry, letter D has one line of symmetry, letter E has one line of symmetry, letter H has two lines of symmetry, letter X has two lines of symmetry, letter Y has one line of symmetry, letter W has one line of symmetry, letter U has one line of symmetry, and letter M has one line of symmetry. So this is all about the theoretical concepts about reflection symmetry, that is, a figure is symmetric about a line, and there are, if we discussed some standard figures about their reflection symmetry and what is their line of symmetry, or how many lines of symmetry they have. Okay, now let's try to solve. Let me see. I hope you can see the problems of exercise 3. This is 18A, exercise 18A. So this chapter Reflection symmetry and rotational symmetry is chapter 18. So let's solve the problems from exercise 18A. Let me zoom a little bit. Okay. So question number 1 to 9 is a MCQ. We have to select the correct choice. Okay. So we are now solving exercise 18A from the textbook of author RS Aggarwal. So question number 1 is that a scalene triangle means a triangle where all the three sides are unequal and also all the angles are unequal. A scalene triangle has no line of symmetry, one line of symmetry, two lines of symmetry, three lines of symmetry. So definitely the answer is choice A. It has no lines of symmetry, because since it is a scalene, all the sides are unequal. There is no regularity of its shape. It is very irregular shape. You cannot draw a line. So that a scalene triangle will look identical on both sides of that line. So a scalene triangle has no line of symmetry. Okay. Problem number 2, it says a rectangle is symmetrical. We have just seen a rectangle is symmetrical about each one of its sides, no. Each one of its diagonals, no. A line joining the midpoints of its opposite sides. So the choice is C. A rectangle has two lines of symmetry, that is, and those two lines are the lines joining the two opposite midpoints of the two opposite sides. So problem number 2, the choice is C, a line joining the midpoints of its opposite sides. Okay. Let's see problem number 3. A square has one line of symmetry, two lines of symmetry, three lines of symmetry, four lines of symmetry. We have already seen while discussing square that a square has four lines of symmetry, the two diagonals and the lines joining the midpoints of the two opposite sides. So it has four lines of symmetry. Okay. Rhombus. Problem number 4. A rhombus is symmetrical about its two diagonals. So a rhombus is symmetrical about each of its diagonals. So the correct choice is B. Always remember that a rhombus is always symmetrical about both of its diagonals. Okay. Problem number 5. A circle has no line of symmetry, no. Two lines of symmetry, no. One line of symmetry, no. An unlimited number of lines of symmetry. So a circle definitely has unlimited number of lines of symmetry, because any diameter of a circle is a line of symmetry, and you can imagine that a circle has infinite number of diameters. A circle has infinite number of diameters because a circle, how many points are there on the circumference of a circle? I cannot mathematically prove that a circle has infinite number of points, but I hope it will not be an incorrect statement if I say a circle has infinite number of points on its circumference. So if it is so, then I can draw a unique diameter passing through a particular point of a circle. So therefore there will be infinite unlimited number of lines of symmetry. Okay. Problem number 6. So problem number 6. What is problem number 6? Okay. So it is saying that problem number 6. It is saying that in triangle ABC, AB equals to AC. Okay. So AB is equals to AC. So if AB is equal to AC, fine. So we have this kind of triangle where AB is equal to AC. So these two sides are equal, and AD is perpendicular to BC. There must be a point D on the side BC, and AD is perpendicular to BC, and BE is perpendicular to AC. Okay. So there is if you draw the line perpendicular from vertex A on the side BC, that is the line AD. So if you draw, uh, also it is saying that if you draw BE perpendicular to AC, PE perpendicular to AC, and CF perpendicular to AB, then ABC is symmetrical about. Oh, okay. So BE is perpendicular to AC. Okay, let this be E, and also let uh, this is F. Now we know that always we have seen while discussing an isosceles triangle that if in an isosceles triangle, if this is an isosceles triangle where AB, if this is an isosceles triangle ABC where AB is equal to AC, then the bisector of the angle A, that is this line, where this is equal to this, the bisector of the angle A is a line of symmetry for this isosceles triangle ABC. And also notice that this line, this bisector of the angle A, this line will also be perpendicular to the side BC. You can easily, we can easily, this is a very popular result, important result in an isosceles triangle. The angle bisector of angle A, that is the angle included between the two equal sides, that angle bisector is perpendicular to the side opposite to the angle which the line is, which the perpendicular is, which the angle bisector is bisecting the angle. So if this is D, then AD will always be perpendicular to BC, where AD is the bisector of the angle A. Now, and so when it is given that in triangle ABC, AB equals to AC and AD is perpendicular to BC, automatically we can say that AD is the bisector of the angle A, and definitely the triangle ABC, the isosceles triangle ABC will only be symmetric about AD and not BE or CF. So the correct choice will be AD. So the correct choice is for C, the correct choice is A. Always remember, in an isosceles triangle, the perpendicular drawn from the vertex A, from the vertex which is from the vertex A, where A is the angle included between the two angles, two equal sides, that perpendicular to the opposite sides will be the line of symmetry. Okay, so in this figure it will be AD is the line of symmetry. Okay, problem number 7. So we have a figure, ABCD is a kite. ABCD is a kite in which AB equals to AD, okay, and BC equals to DC. The kite is symmetric, the kite is symmetrical about the diagonal. Definitely we can say the diagonal AC. The diagonal AC. The choice is A. Definitely it will not be if this is the kite. Let me approximately draw the kite. So if this is the kite, so this side is equal to this side. Let's say A, B, C, D. This is the kite. AB is equal to AD and BC is equal to CD. We know that the diagonal, the kite ABCD will be symmetrical about the diagonal AC and not the diagonal BD. Now, by looking at the figure, you can easily say that the diagonal AC will be the line of symmetry. But what is the mathematical reasoning, which I am not able to say right now, as of now. I will try to look into that and come up with the mathematical reasoning in some future videos. So for this kite, for this given figure kite, we can clearly say that AC, the diagonal AC is the line of symmetry for the kite ABCD. Okay, problem number 8. the letter O of the English alphabet, which is basically you can consider it as a uh, not a circle, no line of symmetry, one line of symmetry, two lines of symmetry, none of this. So it has two line of symmetry, because if you consider O, the O is more or less the English alphabet O is more or less like an oval or ellipse. So I don't know whether I will be able to draw an ellipse or not. Okay. So if you consider this as an O, clearly we will have two line of symmetry. If this is the center, this will be one line of symmetry, and the other line of symmetry will be a line perpendicular to this line. If this line is L1, which is a line which is a horizontal line passing through the center of the letter O. If you consider not center of the letter O, if you consider the letter O as an ellipse or an oval, if the center be O, so a line L1 which is horizontal and passing through the center O, it will be a line of symmetry, and also the other line of symmetry will be a line perpendicular to L1 passing through O. So this will be the other line of symmetry, and definitely L1 and L2 are perpendicular to each other. So the letter O of English alphabet has two lines of symmetry. Problem number 9. The letter Z of the English alphabet has no line of symmetry, two lines of symmetry, one line of symmetry, none of this. I think as the letter Z has no line of symmetry, because if you consider, let us roughly draw the letter Z. Now, does it have any line of symmetry? If you draw a line, let's say, so we have, what is a Z? We have two parallel sides. Let's say if the Z, if I A, B, C, D, let's say the Z is ABCD. AB is parallel to CD. If we try to analyze the figure, how the letter Z is produced, AB, segment AB is parallel to CD. Now, if you draw a vertical line passing through the midpoints of AB and CD, will it be let's say this line, let's say L1, this line, let's say it is passing through the midpoints of AB and CD. So E is the midpoint of AB and F is the midpoint of CD. Now this line L1, is it a line of symmetry for the letter Z? Can you say that the portion of the letter Z to the right hand side of the line L1 is equal to or congruent to the portion of the letter Z to the left hand side? No, I don't think so. Let me see. Now a letter Z, what is the shape to the right hand side of the L1 to the right hand side of the letter Z? What is the shape of the part of the letter Z to the right hand side of the line L1? What is it? It is not a. It is a broken line, broken shape. We are not having any getting shape. But if I draw a line parallel to AB and CD, but passing through the midpoint of BC, I guess this will also be the midpoint of BC. If I draw a line parallel to this AB and CD, let's say this line PQ is parallel to AB and CD, and it is also passing through it is also bisecting the side BC of the segment BC. Now, will PQ be a line of symmetry? uh, mm, Z, this line L2 to me looks like it can be a line of symmetry, because the part of the letter Z above the line L2 is something like this, and the part of the letter Z below the line L2 is something like this. So definitely this is equal to this is equal to this, and this angle is also equal to this angle. So can we say these two figures are this can we say that this figure and this figure, are they congruent? If they are congruent, then we can say that the line L2 is a line of symmetry of the letters Z. Now how do we, now these two figures they are not closed. I mean, even though it has two sides equal and its included angle is also equal, maybe they are, it looks like they are congruent. So the line L2 to me looks like it is a line of symmetry for the letter Z. L2, the line L2, that is the line L2 is parallel to AB and CD, and it is bisecting the BC segment BC. Now, because if you so let's say if this so we have drawn the upper part of the letter Z, the part of the letter Z above the line L2. Let's say this is that the part 1, which is the part of the letter Z above the line L2, and this is the part of the letter Z below the line L2. Now, if you flip the figure 2 vertically, not vertically, horizontally, this if you flip this figure horizontally, I am writing in short H, horizontally, it will become something like this. Now, so this, let this be figure 3, and now this figure 3, you can now see that this figure 3 and 1 looks quite congruent, look quite identical. If you join them, it will make M, it will make the letter M, and we know that letter M has a line of symmetry. Letter M has line of symmetry. So I think L2 will be a line of symmetry for the letter Z, but I am not sure about the line L1. The line L1 is a vertical line which is basically passing through the midpoints of the AB of the segments AB and CD. Will it be a, maybe it is, maybe L1 is also a line of symmetry, I am not sure. So for problem number 9, I am not sure, it could be 2 or 1, I am not sure. So 9, I am not sure, B or C. Most probably it is C. Okay. Problem number 10. What is problem number 10? Draw the line or lines of symmetry of each of the following figures. Okay. So we have the first figure is a quarter of a circle. So it's not a semicircle, it's 1/4 of a circle. 1/4 of a circle, which means that these two lines are equal and they are perpendicular to each other. So AB and BC are perpendicular to each other, and AB is equal to BC. AB is equal to BC. Now, if you draw this R, so this is the figure. Now, what could be a line of symmetry of this figure? Definitely, the line of symmetry will be the bisector of the angle B, bisector of angle of the B, that is the line, this line, the line which will bisect the right angle B, this line PQ, let's say this line PQ, which is passing through the right angle vertex B, and this line is bisecting the angle B. That is, this angle is equal to this angle. They both are 45 degree. So now PQ is a line of symmetry for the given figure. It is a line of symmetry. Okay. So I guess this figure has, that is a quarter of a circle, has one line of symmetry. Okay. What about this figure? It is something like this, this. So I guess, okay, and we have this and this. So I guess these two sides are equal. This side is equal, and this is a right angle. So if this figure is A, B, C, D, and E, we can clearly see that AB is parallel to ED. AB is equal to ED, and also BC is equal to CD. Now definitely the line parallel to AB and ED and passing through the point C, this line will be the line of symmetry. This line will be the line of symmetry. That is the line passing through the point C and parallel to AB and ED. So it will have one line of symmetry. Okay. Figure 3, what is the figure 3? Figure 3 is something like this. We have this kind of figure. This kind of figure. This kind of figure. So definitely it will the line of symmetry. So if this figure, if we name this as A, B, C, D, and E. So what are the features? What are the characteristics of this figure? So this is rectangle, 90 degree. Sorry, right angle, and this is equal to this. Of course, this will be equal to this, and this will be equal to this. And if you and also let's say this be, let's say P and Q, we have EP parallel to DQ, and if you draw a line passing through the point B parallel to parallel to EP and EQ, this line, this will be the line of symmetry for this figure. That is the line passing through the point B parallel to EP and DQ. So this is the point P. EP and DQ are parallel. So if you draw a line passing through the point B, this is the point B, and parallel to EP and DQ, that line will be a line of symmetry for this figure. Okay, and this is the last figure is across a plus sign, not a cross, a plus sign. So this is now this will be a little difficult to draw. Let me see if I can. Is a plus sign. Okay, so more or less this is the given figure. It's a plus sign. Now definitely if you consider this as the center of the figure, and let's say if I name the corners A, B, C, D, E, F, G, H, I, J, and K. So definitely, what will be? How many lines of symmetry are there? Hmm. Hmm. I think there are four lines of symmetry because one line will be the vertical line that will, if this is the center O, if this is the center O, this is the center O, a line passing through. So AB, so we will have AB parallel to GF. We will also have JI parallel to DE. So a line passing through the point O and joining the midpoints of AB and GF, midpoints of AB and GF, precisely the line, this line, this line, I'm calling this line L1. This will be a line of symmetry for this figure. That is a line passing through the center of the figure O and also passing through the midpoints of the sides AB and GF. Similarly, this line will also be a line of symmetry passing through the center O and uh, passing also through the midpoints of the side JI and DE, whereas where we know that JI is parallel to DE. So we got two line of symmetry. Now also there will be two other line, that is uh, if this is the point L, the line a line, let's say line KOL, let's say this is L3, it is also a line of symmetry. This is also a line of symmetry, LOS, I mean short writing LOS, which means line of symmetry. KOL, also line, COH, let's say this is L4, will also be a line of symmetry. KOL and COH, that line will also be a line of symmetry. So it has four lines of symmetry. Okay. That was question number 10. Question number 11. Which of the following statements are true and which of them are false? So these are true and false statements. Okay. Let me see if you can clearly see the question paper. Okay. Question number 1. A parallelogram has no line of symmetry. A parallelogram has no line of symmetry. This is true. This is true. So a parallelogram is something like the two opposite sides are parallel. The two opposite sides are parallel, and also the two opposite sides are equal. Now this, a parallelogram has no line of symmetry. Now its diagonals, the diagonals cannot be a line of symmetry. The diagonals, parallelogram. Parallelogram. What can be? The diagonals, can the diagonals of a parallelogram be line of symmetry? The diagonals. I mean, So let's say if this is a diagram, this is a parallelogram A, B, C, D. AC, the diagonals AC will be a line of symmetry only if we can prove that the triangle ABC is congruent to triangle ADC. Can we prove that? ABC, triangle ABC and triangle ADC, the common side is C, AC. And the diagonals not necessarily, the diagonals not necessarily bisect the opposite angles, no. So yes, the diagonals, of course, the triangle ABC, we must have in a parallelogram ABCD, we must have ABC is congruent to triangle ADC. But how? AC is a common side. AC is a common side. AC is a common side. AC is equal to AC. What else can we have? In the triangle ABC and ADC, what can we have? We can have for triangle ABC, we can have triangle CAB is equal to triangle ACD. Okay, so this angle is equal to this angle, and AC is the common side, and also we know that AB is equal to DC. So we are having a kind of SAS congruency. Congruence criteria is satisfied for the triangle ABC and triangle ADC. So AB is equal to DC and this and this. Yeah, SS side angle side congruency is satisfied. So definitely triangle ABC is congruent to triangle ADC, which clearly means triangle ABC will be identical to triangle ADC, and AC will be a, definitely then AC will be a line of symmetry. So based on this, we can also say the other diagonal BD will also be a line of symmetry. So the two diagonals in a parallelogram are definitely two lines of symmetry. So it is saying that a parallelogram has no line of symmetry. No, this is false. This is false because two diagonals, because a parallelogram is symmetrical about two diagonals. Two diagonals, because let's properly draw a parallelogram and see what is happening. Let's say if I have this kind of parallelogram, so this is a parallelogram A, B, C and D, and these are the diagonals. These are the diagonals. So is the parallelogram symmetrical about AC? Symmetrical about AC. I think because if AC, if we consider AC as the line of symmetry, then the one half of the parallelogram will be the triangle ABC, the other half will be the triangle ADC, and I mean what I'm trying to say is that we can show that triangle ADC is congruent to triangle ABC. From this we can say that AAC is a line of symmetry. By the same logic, we can say that BD will also be a line of symmetry. Okay. So this is false. We can clearly see the diagonals are line of symmetry in a parallelogram. Number 2, an angle with equal arms has its bisector as the line of symmetry. An angle with equal arms. Okay, so an angle. So whatever an angle be, let's say, they say this be an arm, this be an arm. The common vertex be O. Let's say OA is an arm, and some the other arm will make some angle. Let's say, but it will be equal to, let's say OB will be the other arm making some angle, but OB will be equal to OA. Now OB. So now it is saying that we have OA equal to OB. Now if we bisect the bisector of the angle O, will this line be a line of symmetry? Let's say this is P and these two angles are equal. Are these two lines of symmetry of, if is the line OP, which is the bisector of the angle O, a line of symmetry of the angle AOB? It is true. It is true. It is true. An angle with equal arms has its bisector. So it is important that any angle has two arms, and where the arms meet at have a common vertex. So if the arms if the angle be AOB and the arms are OA and OB, so the bisector of the angle at the common vertex, that is O, that will be a line of symmetry only when the two arms are equal. Only when the two arms are equal. So this is true. Number 3, an equilateral triangle has 3 lines of symmetry. We have already seen this is true. 4, a rhombus has 4 lines of symmetry. No, this is false. A rhombus has 2 lines of symmetry. A rhombus, once again, yes, a rhombus has 2 lines of symmetry, which are the diagonals. The 2 diagonals of a rhombus are its 2 lines of symmetry. So a rhombus has 2 lines of symmetry, which are its diagonals. So part 4, the statement is wrong. It is saying that a rhombus has 4 lines of symmetry, but actually we know that a rhombus has 2 lines of symmetry. Part 5, a square has 4 lines of symmetry. This is true. The 2 diagonals and the 2 lines joining the midpoints of the 2 opposite sides. So 4 lines of symmetry a square has. So this is true. 6, a rectangle has 2 lines of symmetry. This is true. A rectangle, the lines of symmetry are the lines joining the midpoints of the 2 opposite sides. So rectangle has 2 lines of symmetry. 2 lines of symmetry. 7, part 7, each one of the letters HIOAX of the English alphabet has 2 lines of symmetry. 2 lines of symmetry. It is saying that the letters H, what are the letters given are H, I, O and X. It is saying that these 4 letters are having 2 lines of symmetry. Now let's see one by one. Now H is something like this. So definitely one line of symmetry will be if this is AB, the perpendicular bisector of AB, that is the line this line. Let's say this is PQ and this is O, where AO is equal to OB, and this is perpendicular. So PQ is a line of symmetry. POQ is a line of symmetry for the letter H. Also AB is a line of symmetry. So definitely H has 2 line of symmetry. The letter has 2 line of symmetry. I, now the letter I, if we consider something like this, if we consider the letter I as something like this, what is this? Something like this, then definitely it will have two lines of symmetry, because a letter I can be considered as a rectangle, can be considered as a rectangle, and we know in a rectangle there are two lines of symmetry, that is the two the lines joining the midpoints of the two opposite sides, that is you draw the line I properly. If this is I will have, let's say, uh, uh, so uh, so the two lines of symmetry will be, if I join the opposite sides, the midpoints of these two opposite sides, this line will be a line of symmetry. This is L1, and the other line, if I join the midpoints of these two opposite sides of this straight line, will be another line of symmetry, L2. So letter I also has two lines of symmetry. What is O? O, the letter O. O is oval. We have already seen the letter O, oval. We have seen that the letter O has two lines of symmetry. If the letter O has the center O, then we can see that the horizontal line passing through the O will be one line of symmetry, and the other line of symmetry will be the line passing through O and perpendicular to the line L1. So letter O has also two lines of symmetry. X also has two lines of symmetry. We have already seen in the alphabets while discussing figures, examples. Where was that? Oh, it was in the notes anyway. So the letter X, you can see, if you roughly draw the letter X. So we know that if the letter X is composed of two segments, AB and CD, and they bisect, actually they bisect each other at the point O. So that is AO is equal to OB, and CO is equal to DO. So the one line of symmetry for the letter X will be the horizontal line passing through the point O. This is a line of symmetry L1, and also the vertical line passing through O. The vertical line passing through O and perpendicular to L1. This is also a line of symmetry L2. So X has two lines of symmetry. So this is a true statement. All the letters H, I, O, X have two lines of symmetry. So 7 is also true. So this brings to an end in solving most of the problems of exercise 18A, which is based on the reflection symmetry. So I hope this video was beneficial to you. If it is so, then please like it, share it with your friends, and once again please support me by subscribing to my channel, and do not forget to press the bell icon so that you will be notified by my future videos. In the next video, I will discuss about the rotational symmetry, and I will solve the next exercise, that is exercise, I guess, 18B. Let me quickly check what is the next exercise. Rotational symmetry. The next exercise is 18B, and after that, okay, so that is the last exercise, 18B of the chapter, reflection and rotational symmetry. So please stay tuned for the next video about rotational symmetry. Thanks for watching, and until the next video, take care and bye.